full screen. Let me know. Can you now?
All good. Yeah.
Okay, I'm gonna stop sharing. Oh, maybe I leave it as it is.
I can do it. Yeah. We have maybe a minute or two away from starting.
Good.
Okay, it's 10:20, so I propose we get started. This session is being recorded, so just for information of all those here, if you're happy with that, that's fine. If you're concerned, then please maybe take care of your video and perhaps your name on the participants list as well. So thanks very much for joining. This is a recorded session, as I mentioned. So this session is about presenting one of the ongoing developments in the quantum flagship project NISQ, which stands for the Next Applications of Quantum Computing. So this is a project, a 4-year one, which is funded by under the Quantum Flagship Program. It's been ongoing since September 2020, and as a part of that, we investigate with partners from academic experts and industrial users a number of use cases around quantum chemistry, optimization, quantum-enabled machine learning, and AI and graph algorithmics. So in this particular session, we are focusing on a particular tool to look at how we can fragment larger molecular systems into smaller ones in order to simulate them and study them on the noisy intermediate scale, smaller quantum computing devices that we have at the moment. So this tool is a classical tool. It's meant to be used in conjunction with the quantum computing enabled simulation of chemistry molecules. So we have with us Dr. Goar Sanchez and Dr. Bruno Chagas from the Irish Center for High-End Computing, ICHEC, who have been developing this tool. We have a first version, so to say, for demonstration and review purposes. So over to you, Bruno and Goar.
Thank you, Venkatesh. As Venkatesh says, my name is Goar. Bruno is here. Today we're going to present Kraken, which is the version, the package that we developed for fragmentation of molecules. I will give like a brief introduction of how we did it, or what is the background of the project, and then Bruno will give all the details about the library, how it's coded, and the functionalities, and do a demo. So why quantum computing? Well, I mean, needless to say that quantum computing is one of the hot topics that we have at the moment nowadays. It's ideally very straightforward, solving very complex problems, and in which quantum computers can tackle things or problems that could be very, very hard or even impossible in classical computing. So that makes this quantum computation very suitable for a variety of applications that can be, for example, artificial intelligence, or weather forecasting, financial modeling, even cryptography, and of course chemistry. Why chemistry? I mean, we can provide with a number of reasons, but mainly chemistry has an infinite number of applications that can go from medicine to pure synthesis to material science. So how do we do it in let's say classical quantum chemistry? What is the approach in a nutshell? Well, what we do is we have the initial coordinates of whatever system that you have. Then you obtain with this coordinate, you obtain the electronic structure, I mean, and structure and the energy. Then with that, you obtain the chemical properties, whatever property that you're interested on. It could be electron density, dissociation energies, whatever. And then once you got these chemical properties, you try to associate it with a physical phenomenon that could be the shape of proteins, the polymer stability, or you can just understand reaction rates or even spectroscopy. So the main important thing is that in order to do all these things, to understand particularly the last 2 points, you need to understand how the atoms and how the molecules interact. So that means that you need to understand what is the intermolecular interaction when you have a kind of a variety of molecules together, how they interact with each other, or what is the intramolecular interaction, which is basically the bond breaking. So, and this is crucial in chemistry. How these two domains mix together, how is the quantum computing and the quantum chemistry mixed together. So few things that we need to take into account is that in chemistry, the number of atoms governs the number of electrons. The more atoms you have, the more electrons you have. Of course, if you have more electrons, then you have more and more spin orbitals, which is an orbital occupied by one electron. And this is related in quantum computing with the qubits in that manner. So the more spin orbital you have, the larger qubits you need. And this is very, very, very important because currently most of the molecules that you can face are simply intractable. You can't, because the number of qubits necessary for those are so big that there's no possibility at the moment to optimize or to treat them in a quantum simulator. So there are a variety of approaches to do that. One of them could be the qubit reduction by different methods, whether you reduce the active space, or in our ideas, it was to use divide and conquer. So one thing that you can do is just to give for any given molecule, you can obtain like a kind of fragmentation scheme. So you can divide the molecule in different pieces. Those pieces can be eventually fit into the quantum simulator, and at the end you can somehow recover the chemical structure, the chemical properties. So our mission in this work package is that our contribution was try to develop a fragmentation tool, a classical one, so a software of a library, if you call it, that for any molecule, any given molecule, or any given number of molecules, it provides with a fragment, whether it's an, I will explain in a second, intra or intermolecular. We are not implementing the pure quantum simulation process that you can do these things, and there are people working on that using DMET, for example. We are one step before, saying that we would like to have this in an automatical way, because if you have to do the fragmentation for a small molecule like water, it's very easy because you have only 3 atoms. But if you are targeting a protein, or you're targeting a whatever molecule that is a carbohydrate, the number of possibilities is huge. So the idea is to do this in an automatic and controlled way. So as I said, this is integrated. This is how our work package integrates with the rest of the work package in NISQ. So the idea is that we can generate a tool that can be used for both the case studies and fit into the people that are developing the more, let's say, theoretical approach. So what we have at the moment is, or we have created, is Kraken, which is a Python library that for a given input, it can do 2 analyses. The first one is the intermolecular analysis, which is we call the clusters. It means the interaction between different molecules. And also it can do the intramolecular, which is the bond breaking analysis. So for a given molecule, analyze every single bond. I'm going to explain this in detail, but my colleague Bruno will give full detail about how Kraken works and how it's designed. So in terms of the inter, intermolecular fragmentation, the idea is that Kraken, for a set of molecules, analyze the molecules, identify each cluster, and then provides with a fragmentation, which is a generation of subclusters until you can have the full isolated molecules. You provide with all these things. In terms of the intramolecular fragmentation, which is the bond breaking, for a given molecule, Kraken analyze the structure of the molecule, identify which are the branches, which are, let's say, the core, and the leaves, and produces a fragmentation in different levels. So you got level 1, in which you have 2 fragments. It means that one of the leaves is removed, or one fragment, let's say, even if it is the core ones. Then you got level 2, you have 3 different fragments with 2 leaves removed, and so on and so forth until you have the full fragmentation. This is done, as my colleague Bruno will show you, in a automatic way, but also you can pick and choose. You can say, okay, I just want to identify, I just want to break this type of bond or this bond. So it's not like a random one. So I think that's the overview of the tool. Bruno, as I say, let's release the Kraken, and he will give you full detail of the library.
Okay, I'll share my screen. Can you see my screen here? This notebook in Jupyter. All clear?
Yeah, it's all good, Bruno.
Okay. So this is the quick start notebook. Once you have access to the repository, you're going to see these quick starts, so you can have all the features that we've implemented. Maybe we're going to update these quick start in order to have all the features. And the Kraken is written in Python 3, and we have 3 submodules for the Kraken. One is the convert, that we're going to explain why we are using this converter. And the second one, and the most important thing, is the molecule. Is a class where we're going to start and initialize our molecule, and we're going to have the fragments based on a graph. And here we're going to convert this chemical file format into a graph where we can run some algorithms over this graph in order to search for fragments and different pieces in this graph. So the third one, and it's a very good one, that's the drawer. So we can explore the connections between the atoms based on this graph. And this kind of tool, we can see what's the scenes behind this graph with this drawer. So the first part is the submodule called converter in this package, where we can convert between certain chemical file formats, because the most used, at least in the most implementation that we can see using Qiskit or Penlane, is the XYZ file, where we see the positions in XYZ coordinates of search of the atoms, but we don't have the connections between the atoms. I can show you like the caffeine molecule. We have in the first column the atoms like oxygen, nitrogen, and carbons. And we have the XYZ positions of those graphs. And with these file, we can construct our Hamiltonian and the circuits and so on. But we don't have this kind of connection where we can construct a graph based on this chemical file format. A more suitable file format is the SDF. This kind of example is for the caffeine. And we have the same kind of properties that we have in the XYZ file, with this column with the atoms and the first 3 columns with the XYZ position. But we have here the connections between the atoms and the type of bond, like the single bond or double bond. So that's a feature we're going to explore with our package. So in the converter, we've been using the open bubble in order to convert these file formats. That's a tool or this package that's very fast in order to convert these file formats. So in the quick start, we can have these function here where we have 3 parameters. One is the path for the file. Second is the input file format, that's the SDF, and the output file format. In this case, we're converting the caffeine molecule from the SDF file into the SMILES, the SMI. The SMI will be a string which contain the characters that simulate the connection between the atoms in this specific way. For example, this symbol here is the double bond, and we have double bond, and it's a bit more complicated to explore using the SMI file, but it's very compact. The second one, the most important for us in our case, is the conversion between the XYZ file into the SDF. Here we are converting the benzene molecule into the SDF. And based on this kind of file format, we can explore our graph theoretical approach. This is the first submodule. As I showed you, we have the converter. Now we have the molecule and the drawer. We have this hierarchy here because the drawer depends on the molecule that we previously started. So the second submodule is the molecule, and we import this class here called molecule. And we just need to start. This is the most important thing that we need to perform when using the Kraken. So we need to have the molecule that's going to be the class with the path for the file and a name. This name is not mandatory, but we suggest you to include that in order to have folders and files named properly. So the most important thing is this molecule class that we need to start. So once you start, we have some initialization that we're gonna have for this molecule, the name of the molecule number. Imagine that we are doing 2 caffeine molecules at the same time, but they have the same structure, but we need to name them in order to access them in different ways. But we have the molecule, the path, and the structure of the graph based on the atoms that will be the vertices in a graph, the edges that will be the connection between the atoms, and the bond's gonna be the type of bond, like single, double, and triple bonds. So in this first one, we have this list of characters for the atoms. Here we have a list of tuples for the edges, and here a list of integers for the bonding type. Another attribute in this class is the graph based on the network X package, where we can have the algorithms. We have the XYZ list because we may use that in different ways, where we can have the fragments and we can get the XYZ position of those fragments. So the third submodule will be where we can draw the graphs properly. So we are importing Kraken.drawer, this third submodule, and we have different functions here. My bar is interrupting me. Here, the drawer. We have this package here with different kind of functions. We can draw the entire molecule, but we can draw just the fragment of the molecule based on the molecule and the subgraph. For example, here we have the caffeine molecule. Now we updated this version because we're gonna have the number of the atoms, because imagine that we need to break the bond between oxygen and carbon, but we don't know if that's oxygen or the second oxygen here. And we can like break 1, 9, this tuple, or we can break 0 and 8 tuple. So with this visualization, we can see the graph behind the scenes using the caffeine. So we have the second function here in order to draw the subgraph or the fragment. So in this case, we are using 0 until 9 is the the center of this graph, plus the 11, that's going to be this carbon here. So we have these fragmentation, the draw of this fragment based on that subgraph. But now we're going to discuss the fragmentation schemes. That's going to be the intermolecular or the intramolecular fragmentation. The first one that we're going to discuss is the intramolecular fragmentation. Imagine that you have the caffeine again, but we need to break the leaves. The leaves in a graph is a vertex which has degree 1 or is connected to just one single atom. In this case of the caffeine, we have the leaves going to be all of the hydrogens plus those 2 oxygens here. And we need to identify using certain graph algorithms, but we just need to find the atoms which has degree 1 in this case. That's going to be our algorithm. So we have this molecule caffeine, that's the class in Kraken. And we have this method called breaking leaves, but we can't define the number of leaves we're going to fragment. It can be just 1, 2, 3, or 4, and up to the maximum. The maximum number of fragments in this case will be 12 because we have 12 leaves here. So we can use the drawer again in order to draw the fragment that's going to be the oxygen and the remaining part of this graph. You might remember that we had a oxygen connected to 9 and another oxygen connected to this carbon in 8. But in this case, the first fragment will separate them apart based on this oxygen and the carbon here. But we can have this other drawing here, this is a break and draw, because based on this fragmentation, breaking this bond, we can have this kind of drawing here. We are highlighting in red the connection between 0 and 8 based on this fragment that you use here. But we can break 2 leaves at the same time, but we are going to have this number of fragments because we are taking the combination between every 2 parts of the leaves. Here we have this oxygen and the other oxygen that we are breaking and separating from the 9 and the 8 in this caffeine molecule. And with this function, we can highlight the connection between 1 and 9 and 0 and 8. If we need to explore another drawer here, we can have this drawing based on the leaves that we have different colors. The green going to be the leaves, and the rest remaining parts of this graph is going to be the trunk of this tree. We are having brown color here. If you need to visualize what's going to be all the leaves in a molecule. And based on the fragments and the molecule, we can convert this molecule based on the Kraken, and we can get the components and put into files that we're going to have here. We have this folder with all the combinations based on the XYZ files. So here we have one part and the second one, but this is for the intermolecular fragmentation, that folder. The intermolecular fragmentation, we're going to search for the components in a graph that are not connected to each other. They're isolated graphs in a huge graph. In this case, we have a file with benzene and CO2s, and we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 fragments, because we have 2 benzenes and 3 CO2s, and based on the same approach, we can fragment and combine them into different parts. And we have the same kind of structure. We have the molecule based on the Kraken, the class, and we can convert the fragments to files like we have here. This combination here is 0. We have 1 benzene, another benzene, CO2, CO2, and another CO2, but we can have different kind of combinations. The combination 2 will be taking 2 by 2. Here we have 2 benzenes for this part. This here, 1 benzene and 1 CO2. And that's the walkthrough, the code. If Gore is here, we can discuss. We are open for questions, and that's all.
Thank you, Bruno. So the ideas we discussed is that to give to provide with this tool and leave it open, so to the rest of the work packages member, and they can evaluate, they can try it out and come back with to us if they have any suggestion on anything that they found, any bug. And that's all. If there is any question now.
Yeah, I have a question. So when you fragment your molecule, when you cut a bond, how are you envision the actual calculation should be run? Because you're cutting sort of in the middle of the wave functions, if you like.
Yeah.
So how do these translate into, actual calculations?
Well, if you use that in chemistry, let's divide it into classical chemistry or classical quantum chemistry and a quantum simulator. If you are doing that in a classical quantum chemistry, depending on the bond that you're cutting, you're breaking, you have to take different approaches. So you could double bond. As I said, this fragmentation tool doesn't lead with any chemical thing. It's just pure fragmentation in a mechanical way. If you're doing chemistry, you have to face that you got a bond. Maybe you have to put the multiplicity if you are cutting up a radical or you're cutting a kind of plus and minus charge. That is on the chemistry side. The calculation, you can do whatever you need. If you try to include dispersion or whatever, if that comes on the method that you use, go to the MP2 coupled cluster, or you move to DFT, whatever functional have that contain any dispersion implicit. If you go to the quantum simulator, that's another business, because quantum simulator, there are a variety of methodologies that you can do. As I mentioned before, DMET is one of them, in which you fragment the molecule and you enclose it in a quantum bath. We are not experts on that field. We know that exists. We have read and explored the idea to further implement these kind of methodologies into the fragmentation tool, but so far what we are having at the moment is the fragmentation tool per se.
Yeah, but if you cut the bond, you introduce a lot of errors in your calculation already at that stage, and you have to compensate for that, even on a classical computer. So I'm not sure if I follow the sort of the benefit of actually doing this fragmentation.
Well, let's say you want to obtain the dissociation energy of a bond, okay? Which is basically, you take a bond and you stretch it to the infinite. Or in another way, is just you take the bond, you break the bond, and the dissociation energy is basically the energy of the whole molecule minus this fragment, which is the energy at the infinite, infinite separation between those. If you have, let's say, a huge carbohydrate, like octane or decane, and you want to obtain the dissociation energy of all, or the proton affinity of all the protons around, you have to do two ways to do it. And this is what we do in chemistry. You take the molecule, I delete one of the atoms, calculate the whole system, this fragment and this fragment. I can do that, or I can use KraChem, and KraChem will prepare all the inputs according to all the things, and then you can automatically feed into your classical software. That's one of the benefits. You save a lot of time and you don't make mistakes. Plus, if you go for further, like, I don't know, like octanes or cyclooctatetraene, I have a lot of hydrogens, you can do that. So your idea is that you can obtain the proton affinity of all the protons in one shot. And then you can pinpoint, okay, this is the proton that is more likely to be removed if a base attack. That's one of the ideas. Another idea is that people that does, for example, fragmentations of small nanoclusters or carbon clusters, the number of possibilities, for example, you take a fullerene, that was years ago, but I did some kind of research on that. You got a fullerene, you have some speed ions impacting in the fullerene breaks into tiny pieces. And then with a mass spectrometer, they analyze the pieces of which fragments of the fullerene they're obtaining. If you want to do this in a classical way, you have to take a fullerene C60 and start to do fragmentations. Okay, I take this, I take that, make small pieces, and then optimize those. It could be eternal. You can take ages, decades to do that manually. With the Kraken, you could provide the fullerene, and you would say, give me all the possible fragmentations. It could be thousands, but Kraken do it in a minute. And then you can fit them into a quantum computer because these calculations are independent, and Kraken organize them into different folders. You can literally submit them into NHPC, taking 1,000 nodes, one job each. And then you will have all the possible fragments and all the possible combinations in a few minutes. That's the benefit. We are not, again, this is quite clear at the very beginning, we are not implementing anything. We are not taking into account the second step, which is the implementing that in chemistry or in the quantum simulator. The idea is to have a tool that can be beneficial for doing these things in an automatic way.
Yeah, I can see the benefit of automating the fragmentation process, but to be honest, we're not going to work on any of those large systems that it's not going to benefit the work we do in my part of the project, if you like.
Okay, I mean,
yeah.
It could be it could be a tool for everyone, but not everyone will use it. We fully understand. The idea is to give possibilities, an open possibility, and actually it's a tool that is not only targeting quantum computing, but try to reach a more general audience like chemistry. I know at least 3 or 4 groups that they will be interested in using that, not in quantum simulation, but in quantum chemistry.
Well, to be honest and transparent, we already have tools like this available in my organization. So yeah, that's why I'm a little bit, wanted to see how we take the next step to actually implement a method that can take advantage of this fragmentation on a quantum computer.
Yeah, that's as I said, that's our next step, and I don't think that it's going to fall under the NISQ project, because I think that we have already burned our contribution to the work package. But it was in our scope. Yeah, actually, for a period of time, we were exploring the possibility to implement our fragmentation tool into a quantum simulator. But as I say, we don't know yet. I know that there are different groups. I know that there are companies working on that. We are aware of that, and we have been in contact with them. But as I say, this is what we'll have for this. We have a small PMs to burn in this work package. So this is the best that we can do.
Yeah.
So sorry, apologies, I have to leave now. If you have any further question, Venkatesh and Bruno will be happy to answer that. And if you have any question, and I'm going to put my email here in the chat, and feel free to drop me an email, and I will be happy to have a follow-up call or an email. Thank you very much.
Thank you, Gowar.
Thank you, Gowar.
And thanks, Santosh, for the comments. Definitely, I think we need to pick up on the conversation within the project as well going forward to see how we can bridge the gap there. So there'll be any other questions?
Venkat, I have a question.
Yeah, sure.
Right. Hello. Am I audible?
Hello?
Yeah, go ahead, Anand.
Yeah.
I can hear you.
Yeah. Interesting. I want to know if there is any export formats of these molecules that you are generating. Like since it's a graph that is output is something like an XML format where you can export this particular file, so that this can be taken to other platforms where bigger graphs can be constructed, more real-time systems can be constructed.
About the graph, they are written with the network X. That's the class that we have this graph, but we can convert into agency matrix or any other representation of this graph. And in respect of the molecules, they are written in XYZ, STF, so we can convert between the most proper format for you in this case.
Okay, thank you.
Thanks, Anand. And if there be any other questions from the attendees here? If not, so thanks very much, Bruno, again, and thanks everyone for being here. We'll record this and we'll edit it and publish it on the NISQ project. Thanks very much.
Thank you very much.